Okay. Good morning, good evening, everyone. My name is Ahmed Sharafuddin. I'm the marketing team leader of the Environmental Club. First of all, I'd like to thank you all for taking the time and joining this webinar. And I'd like to thank Dr. Ali Al-Awami for presenting this webinar, where he'll be talking about the hydraulic economy and sustainability. He's an assistant professor at the electrical engineering department at KFUPM. If you all just allow me to introduce the club real quick. With the KFUPM Environmental Club, our mission is to raise awareness, bring about the necessary change in attitude. Bring about the necessary change in attitude and provide students with opportunities to take action in protecting, restoring, and improving the environmental quality in Saudi Arabia, King Fahd University of Petroleum and Minerals in particular. Our vision is to play and fulfill a prominent role in the 2030 vision by providing a healthy, clean, and protected environment, supporting a sustainable world for all organisms, now and for future generations, based on a society living in harmony with nature. Our leaders are Hussein Abu Mnassar, the founder and advisor of the club, Faisal Al-Hajri, the president, Walid Al-Zahrani, the vice president, Hassan Filimban, operation leader, Abdurrahman Yusuf, documentation leader, Ahmed Sharafuddin, that's me, the digital marketing leader, Turki Rashid, human resources leader, Ahmed Suleimani, research leader, Salman Hamiduddin, public relations, and Abdullah Namla, design leader. And that's it for now. Dr. Ali, the floor is yours, if you may. Let me just stop sharing my screen.
Okay, thank you very much, Ahmed. Let me start by sharing my screen. Let me do this. Do you guys see my screen?
Yes, clear, Doctor.
Yeah.
Yes.
Okay, great. Assalamu alaikum. Thank you, everybody, for joining. What we're going to do today, I'm going to walk you through hydrogen and hydrogen economy and how it's related to sustainability and how it promotes sustainability. Hydrogen is basically an enabler for sustainability, as we're going to see. It's kind of a 360 degrees talk that is going to touch upon the basics. I don't think we're going to have a chance to dig in depth in any of any individual topic, but well, let's give it a shot and see how it goes. Feel free to stop me and ask questions or put questions in chat. I don't think when I'm presenting I'll be able to check the chat screen, but maybe Ahmed can help me if there is a question in the chat that needs my attention.
Yeah, sure, Doctor. For me, I think it's better if we just leave the questions for later on when you finish the presentation, so we can collect all the questions and then present them to you. What do you think?
Fair enough, no problem.
Okay, good.
All right, so let me start with this chart that shows that hydrogen matters. So this is a chart that was developed. It's kind of a prediction for hydrogen consumption levels up to 2050. That's produced by the Hydrogen Council, and shows that hydrogen demand could increase by up to 10 times by 2050 compared to 2015 numbers. So in 2015, we only consumed this much hydrogen, and 2050, we have this big column. And if you think, well, this is kind of a prediction, maybe it's true, maybe it's wrong. If you look at the history, if you look back instead of looking forward, you see that hydrogen demand has increased threefold since 1975. So hydrogen demand is increasing. It has been increasing for the past several decades, but it is expected to increase at a much higher rate in the next few decades. So what is good about hydrogen? Why hydrogen specific? Hydrogen is probably the most abundant element in the universe. If you're talking about Earth, Earth is 2/3 water, the surface of Earth, and water is 2 atoms of hydrogen and 1 atom of oxygen. So that's plenty of hydrogen out there. It is also compact. So if you extract hydrogen, for example, from water, you can compress that and you can store a lot of energy in a very small volume. So it's a very compact energy resource. And it is odorless, if that's something that would bother you, or would, I mean, if you care. But it doesn't smell. Now, what is hydrogen used for? Hydrogen, most of the uses for hydrogen so far are these purple bubbles. So these are kind of the industrial applications for hydrogen. Hydrogen is used to produce ammonia, which is a huge industry. And by the way, Saudi Arabia is one of the largest producers for ammonia in the world. So it is a big industry over here. Hydrogen is used for metal refining. If you'd like to extract steel, you need, you can use hydrogen. So it's used a lot. And it is used in many other industrial applications. But that is not where hydrogen is used. That's not only where hydrogen is used. Hydrogen is used for heating. You can heat up, you can use it as fuel. So you can burn hydrogen and get heat out of it. You can use hydrogen to synthesize fuels. So combining hydrogen with CO2, actually, you can produce methanol. You can produce gasoline. So it's, and that's a big plus also, actually, because that will consume some of the CO2. So that will help them with preserving the environment. It can be used for hydrogen cars, hydrogen vehicles. There is a lot of talk about pros and cons for hydrogen vehicles compared to, let's say, conventional vehicles or even electric vehicles. But this is one use of potential use for hydrogen in the future. And so on. So there are a lot of uses for hydrogen, and it seems that as time goes, people are finding other applications and expanding the existing applications. You are going to see that this chart is actually, I'm hiding half the chart. I'm showing only one half of it. The other half of it, I'm going to show in a few minutes. Okay, in fact, hydrogen is an energy carrier. So what does that mean? So let me, if you look at the right-hand side here, these are all the applications that require energy. So we use energy for appliances, for electrical appliances. We use it for transportation. We need fuel. We use it for industrial fuels. We use it to produce chemicals. So these are all the different applications that require energy. Now, where is the energy coming from? It's coming from the left here. So energy can come from fossil fuels, oil, natural gas. It can come from nuclear reactors. It can come from renewables and other means of producing energy. Now, how do we get energy from the supply to the end use? How do we get energy from the left-hand column to the right-hand column? Typically, we use electricity. So we convert fossil fuels to electricity through power plants, burn fossil fuel, produce electricity, transmit that electricity through long distances, and then use it on the right-hand side for electrical appliances, for transportation, and for industrial uses, etc. You can replace electricity by hydrogen, or you can complement electricity by hydrogen. You don't have to replace it 100%. You can complement it. They can work together. We are going to see that actually they can work together pretty well, hand in hand. Now, in some cases, hydrogen can even beat electricity. Now, I'm coming from an electrical engineering background, and I dare to say that. So sometimes, honestly, hydrogen can beat electricity, but very often electricity is a better carrier. Okay, so it depends on the circumstances, but when they work together, they can do wonders. So an example where hydrogen can beat electricity is this, what you see in this colored picture. So on the left, you have renewable resources. On the right, you have consumers for fuel, for energy. And in the middle, there is water. So let's say there is the ocean in the middle. So now we'd like to we are producing energy on the left-hand side, and we are consuming it on the right-hand side. And we'd like to transmit that energy from the left to the right. So we can use transmission lines, we can use electricity, underground cables, marine cables underneath the ground, which are being used in many parts of the world. But for that application, hydrogen looks as a very feasible alternative. You can turn the power produced or the energy produced by wind and solar, you can turn that into hydrogen, you can ship that hydrogen, and then you can turn it back into whatever energy form you'd like on the right-hand side. So sometimes hydrogen actually has an edge. Now that we mentioned electricity, given that my background is in electrical engineering, I cannot escape to talk a little bit more about electricity. So you guys are probably aware that according to Vision 2030, the Kingdom of Saudi Arabia is targeting to produce 58.7 gigawatts of electric energy from renewable resources. And if you are wondering how big that is, today's generation capacity in the kingdom is 70 gigawatts. So that if you put all the generators in the kingdom together, if they're all running together simultaneously, they are able to produce about 70 gigawatts of power. Now, by 2030, the expectation, the prediction is that, or the target is to have up to 120 gigawatts of generation capacity kingdom-wide. Out of the 120 gigawatts of generation capacity, about 60 gigawatts are going to be coming from renewables. So renewables are going to form about 50% of the total generation resources. So that's huge. Now these renewables are going to be scattered everywhere. They're going to be mostly solar PV, solar photovoltaic resources, but there will be some wind, and there will be a little bit of CSP, concentrated solar power. Now, wind is clear what wind means. You produce electricity from wind. The difference between solar PV and CSP is that in solar PV, you convert the light in the sun into electricity. And in CSP, you convert the heat produced by the sun, the heat received on Earth. You convert that heat into electricity. So the focus more in Saudi Arabia is on solar PV, but there will be some small capacities of CSP also. And there will be also some wind. Now, the challenge with the renewables is that they require a lot of flexible resources. What do I mean by that? This curve that you see in front of you is called the net load curve for multiple years, for a typical day in the year. So x-axis is time, 24 hours, and y-axis is the electric load consumption in California. This is taken from California ISO, California System Operator. And this is actually not the load, this is the net load. And what the net load is the load minus the solar PV power output in California. So net load is equal to load, the electric load in megawatts, minus solar PV outputs. That's the net load. Now, why does that matter? It is the net load that needs to be met with the other generators that are not renewable generators. There is some wind, but not as much as solar. So if I have an electric load, say, of electric load, and my solar is producing 10 gigawatts, 30 minus 10 is 20 gigawatts, that's the net load. That is how much I need to produce from non-renewable resources. So that really matters for me. Now, if you look at the 2013 curve, the blue curve over here, it is kind of a nice curve. You get the load increases at about 7 or 9 or 8 p.m. because of lighting and everything, people start cooking and so on. So that's an evening peak. Now, during the daytime, the net load is reasonable. The load would have looked something like this. But because solar will produce a lot during daytime, the net load, which is the load minus solar, is the blue curve that is shown over here. Okay, so solar is good. It is reducing our peak demand, which is around noontime. It is not able to reduce our peak demand in the evening. But that's fine. At least it's helping with the peak demand in the noontime. Now, what happens if you have a lot of solar PV, and that is what is happening in California? The PV penetration has increased in the past several years. The net load looks like this brown curve in the bottom. So what is the problem with this curve? This curve shows that during daytime, actually the net load is at its minimum. So load minus solar PV is at its minimum. That's not a problem. The problem is if you compare the minimum with the peak, you get this huge variance, huge difference. And the difference amounts for about 12,000 megawatts. So 12 gigawatts, okay? That's in 2020. If you compare that with 2013, when there was not a lot of solar in California, the difference between the minimum and the peak is about 6,000 only, 6,000 megawatts. So why does that difference matter? That difference is what requires flexibility. You need flexible resources that are able to produce up to 12 gigawatt, that are able to increase their power output by up to 12 gigawatts very quickly in a matter of few hours in the evening. If you don't have solar, or if you have very little solar, the ramping capacity, the capability that is needed is only 6,000 megawatts. So incorporating a lot of renewables requires a lot of flexibility. Okay, that's a case for solar PV. The case is even worse, or the need is even more if you have wind instead of solar. So this chart shows you a system. The x-axis here is about 1 week, and the red curve is the load curve. This is not net load. This is just the load, okay, the electric load. And you can see that it is very cyclic. Every day, the cycle repeats itself. So it's very predictable load profile. This is the red curve. The green curve, however, is the wind power output in that system. And you can see that wind is going all over the place. And sometimes wind increases when you are not interested in a lot of energy. And sometimes it decreases when you are really interested in a lot of energy. So if you look at this area, wind is dropping during the time when load is increasing. So wind is dropping when you need it the most, okay? And that results in a mismatch between generation and load, between generation and demand. And that mismatch needs to be met by other resources. For this specific system, they are lucky that they have a lot of hydro. This blue line represents hydro generation. So they have a lot of hydro generation, so they're able to ramp up generation from hydro to compensate for the wind ramp down. So they are lucky. We don't have hydro in Saudi Arabia. So if we were to do this over here, if we were to integrate a lot of renewables, a lot of wind, we need that flexibility. Most of our generation is thermal generation. They do not provide that much flexibility. They are limited as far as flexibility is concerned. So to mitigate for this challenge that renewables are bringing about, we need storage. So if we can store energy, so that if wind blows or if we have a lot of solar energy, we can store it, and then we can use it whenever the sun goes down or whenever the wind speed slows down. So storage becomes very important. And there are different ways of storing energy, different technologies, using batteries, using pumped hydro storage, and so on. Everyone has its own advantages and disadvantages. One of them is hydrogen. So you can use hydrogen. You can store, if you have plenty of renewables produced with your renewable resources, you can convert the additional unneeded renewable production into hydrogen. You store it, and whenever you need it, you can convert that hydrogen back into electricity. You can use fuel cells to do that. So now I come back to this picture that I started with, and let's put the pieces of the puzzle together. So now on the right-hand side, you see the hydrogen, and on the left-hand side, you see the electric power system, and you can see that they can work pretty well together. So you are producing renewables, you're producing electricity either from fossil fuels or from nuclear plants or from renewables. And all that power is injected into the electric power system. And well, there are electric loads that are going to consume a lot of power from the electric power system. But maybe during the time when there is excessive amount of energy that we are producing, especially from renewables, because some of these renewables are not predictable or they are not controllable. So if you're producing a lot, more than we need, we can store some of that energy into batteries, or we can store it into hydrogen. And whenever, so we run that into a hydrogen generation plant, maybe using electrolyzers. So this is an electrolysis process. We're going to talk about it in a few minutes. And then we produce hydrogen. And whenever we need that, we need to produce more electricity, I can use some of that hydrogen back using fuel cells. So that is a reversible process. I can go from electricity to hydrogen using electrolyzers. I can go from hydrogen to electricity using fuel cells. The good news is the reason why hydrogen is different from any other storage device is that hydrogen itself is a very valuable product. So when I convert electricity to hydrogen in this phase here, going from here to here, I came up with a very valuable product. I don't have to convert that back all to electricity, because I can use that hydrogen for industrial processes. I can sell that hydrogen to an ammonia plant. I can sell that hydrogen to hydrogen fueling stations. I can synthesize fuels back from hydrogen. Okay, so it is a very valuable product. I'll see many people interested in buying my hydrogen. Okay, if I want to bring some of that hydrogen back to electricity, I can also still do that. And that's why when we talk about hydrogen, we don't talk about hydrogen as a storage medium, period, but we talk about hydrogen as a full economy, a complete economy that has all the different levers of an economy. So it has multiple uses. It is a very valuable product. I can sell it, I can use it, I can convert it to ammonia, I can convert it to many other things, and I can convert it back to electricity. So that's how these two systems can work very well together. We mentioned fuel cells. Fuel cells is the means to produce electricity from hydrogen. So if I go back here, this is actually a fuel cell. So that will take hydrogen, will take oxygen, and it will produce for me electricity where I can connect my load to it. Fuel cells, they have advantages, of course. They produce zero CO2. There is no rotary machinery, so there is no rotating parts in fuel cells. So they are very their noise level is very little. They don't produce noise, and they don't produce CO2. So they are excellent. Okay, so now, it seems that hydrogen is a very interesting product. How do we produce hydrogen? We just mentioned that you can produce hydrogen from electricity using electrolyzers, but this gives the full picture here. So most hydrogen today is actually not produced using electrolyzers. It is not produced from electricity. The vast majority of hydrogen produced today in the industry is produced from natural gas. So you take natural gas, you pass that natural gas into a steam methane reformer, and then you produce hydrogen. And those in the audience who have a chemical engineering background, I'm sure they know much better than me about this. The bad news here is that if you use natural gas to produce hydrogen using steam methane reforming, you produce a lot of CO2. So you emit a lot of CO2 to the environment. Not very welcoming news. That's why it's called gray hydrogen. Now, you can work, excellent chemical engineers, very brilliant engineers, they are working on improving this process so that the CO2 that you emit is very concentrated to the point that you can actually capture it and store it. That's called blue hydrogen. So the difference between blue hydrogen and gray hydrogen is in the fact that you modify this chemical process so that the CO2 produced is concentrated. It is easy to capture and can be stored, or it can be used. By the way, you'll find people buying your CO2. If you produce very pure, very nice CO2, go to Coca-Cola, go to Pepsi company. They will buy your CO2. They put it in their soft drinks, right? Go to Saudi Aramco. They will buy your CO2. They inject it into the oil wells for enhanced oil recovery. So the people will be interested in buying your CO2. So that's called blue hydrogen. So that's kind of what is presently being done, okay? Hopefully in the future, we can transition from gray to blue, all the way to green, where we don't need natural gas at all. And we can produce hydrogen from green resources like solar and wind, or whatever other renewable resources. That will give hydrogen with zero CO2 emissions. I talked about this already, so I'll just skip through this. Now, I'm showing here the electrolysis process. So you can see here that you need an electrolyzer. And the electrolyzer is just, if you can think about it as 1 over the fuel cell. It is a fuel cell that's working backwards. That's the electrolyzer. And for the electrolyzer to work, it needs 2 things. It needs water. So we need to inject water here. So that's water. And you need electricity. And you can get electricity from any resource. But if you want to make it green, you need a green resource. So from wind or solar, you inject that into the electrolyzer. It will turn water, H2O, into hydrogen and oxygen. Hydrogen can be compressed, and oxygen can be also compressed, and you'll find people interested in buying your oxygen. So that's how electrolysis process goes. Okay, why don't we do green hydrogen? What is wrong with green hydrogen? It is still very expensive. So this chart here shows, roughly speaking, cost of producing hydrogen in US dollars per kilogram of hydrogen. If you use blue, this is gray hydrogen on the left. This is blue hydrogen using natural gas. And this is blue hydrogen using coal. And then this is green hydrogen from renewables. So you can see that there is a big difference in price. So yeah, that we need to work on that a little bit. But I'm bringing some good news tonight. Good news number 1 is that we have a competitive edge in the Middle East. If you look at the numbers here, this is comparing different countries or different regions in the world as far as gray and blue hydrogen. This does not include green hydrogen. This is only gray and blue hydrogen. So you can see that Middle East cost of producing hydrogen is the lowest in this chart. And the main reason for this is that there is plenty of natural gas. This is the cost of natural gas. This is the added cost that comes from natural gas. So you can see, because we have plenty of natural gas in the Middle East, then we have a competitive edge. Well, good news number 2 is that green hydrogen is also the price for, or the cost of producing green hydrogen is dropping, and it's dropping very quickly. And the reason for that is that renewable cost is dropping very quickly. This chart here shows how the renewable cost has dropped. It's called levelized cost of energy, how the levelized cost of energy has dropped in the past decade or so for different renewables. So gray is wind, and wind is actually has been very competitive in the past few years. Okay, yellow is PV, and you can see how PV cost is dropping very, very quickly, and that is expected to continue for the next coming years also. So renewables cost is dropping, which means that green hydrogen is gonna have some interesting future. According to a study conducted by DNVGL, which is a very well-known consulting company, they expect green hydrogen to become a competitive alternative by 2035. Competitive alternative means compared to gray and blue hydrogen. So 2035 is not too far away. So if it ends up being competitive, you will see the hydrogen economy blowing up really quickly. Okay, now let's switch gears. How do we store hydrogen? Now, if we are gonna use hydrogen as storage medium, then we need to store that gas. Now, storing gas is not easy. So that's a big challenge. So we can either compress hydrogen and store it. So you can see here in the figure, you can see vessels where compressed hydrogen is being stored, or can be converted into a liquid like ammonia or methanol and can be stored. That will make storage a lot easier because it's not gas anymore. So you can store in huge volumes. Or it can be even stored as a solid, in a solid form. So this is kind of a hydrogen battery, if you like. So next, I'm going to show a few examples where hydrogen is being taken seriously, let's say. So I'll start with the NEOM project. And NEOM in the Red Sea on the west coast of Saudi Arabia, they are building a green hydrogen infrastructure, huge green hydrogen infrastructure actually, that is based on electrolysis. So what we have over here, we are going to have a lot of wind and solar, and then that will go into an electrolyzer to produce hydrogen. And that hydrogen, it's going to be in NEOM, which is, you know, a small island in the Red Sea. So you are not going to find a lot of customers interested in buying all that hydrogen. There is going to be plenty of hydrogen. So that hydrogen will have to be shipped elsewhere. So in order to ship that hydrogen, it will be converted into ammonia, into a liquid form. And to do that, ammonia is made of 1 atom of nitrogen and 3 atoms of hydrogen. So we need nitrogen. And nitrogen is going to come from an air separation unit that also requires electric energy. And that electric energy will come from the renewable resource on the left. So the renewable resource will feed up the electrolyzer and will feed up the air separation unit. The electrolyzer will produce hydrogen. Air separation unit will produce ammonia. Air separation unit will produce nitrogen. The ammonia reactor will combine hydrogen and nitrogen to produce ammonia. That ammonia is in liquid form. It will be shipped using shipping vessels, using ships, and it will go different parts of the world. When it reaches to a final destination, hydrogen can be converted back, can be extracted from ammonia, and then can be used to fuel transports and for other industrial uses, or ammonia itself. Again, ammonia is used in fertilizers and so on. So some of that ammonia will never be converted back to hydrogen. So this is a huge project. A few numbers about that project. It is expected to produce 650 metric tons per day of hydrogen. The renewable resources have a capacity of 4 gigawatts, 4,000 megawatts. That is as big as 4 nuclear power plants. That's huge. It will cost $5 billion, the hydrogen plant, and that does not include the distribution facilities. The distribution facilities will cost an additional $2 billion. Air Products is leading that, and a couple of other companies. The ammonia produced is gonna be about 1.2 million tons per year of ammonia. Every 1 ton of ammonia consists of 177 kilograms of hydrogen. So that's a huge project, a very ambitious project that's expected to come the next few years. And we are not alone. In Germany, they are building this huge infrastructure to produce green hydrogen and to distribute it using natural gas pipelines. So they are not going to ship hydrogen using vessels or using trucks, but rather they are going to use the existing natural gas pipelines, they will inject hydrogen into it, and they will use it for distributing hydrogen. That has its own challenges, of course. Hydrogen is a lot more explosive than natural gas. You need to be really careful when you do that. So when people do that, usually they do it in stages. They inject only 5% hydrogen, they increase it to 10% and so on. They do it in small increments to make sure that the natural gas infrastructure will be able to deal with that new gas, which is hydrogen. I'll skip that. In Australia, they are thinking also along the same lines. They are going to use renewables in order to produce hydrogen using electrolysis, and then they will convert that hydrogen to ammonia. Some of that hydrogen actually will stay in its gas form. It will be distributed within Australia using natural gas networks, and then some of the hydrogen will be shipped overseas after it is being converted to ammonia. And the EU, they have big vision for hydrogen. They are planning to produce 6 gigawatts of hydrogen from electrolysis, green hydrogen, by 2024. That number is expected to increase to 40 gigawatts by 2030. And that number is expected to go even beyond that after 2030. The Japanese have a very interesting, I'm about to end here. The Japanese have a very interesting approach. Instead of going big, they are going small. So they are doing distributed hydrogen. So they build small electrolyzers, and they install these electrolyzers in the hydrogen fueling stations. So if you have a hydrogen electric car, you go to the fueling station. The fueling station itself has an electrolyzer, and it has renewable resources. So everything is local. So renewable resources in or near the fueling station, and then an electrolyzer local in that place. And the electrolyzer is producing hydrogen locally, and that hydrogen is being used is injected into cars or whatever. I'm towards the end, so I left this boring definition that's usually used at the beginning of presentations, definition of what hydrogen economy means. I left it to the end. I thought you might be more interested in pictures and figures, so I left this toward the end here. Done. Thank you guys very much. I'll be glad to take questions.
Well, thank you very much, Dr. Ali, and thank you for this insightful webinar and sharing with us this valuable information on hydrogen economy and sustainability. We actually have a few questions already asked, if you may. We have the first question from Saeed Abdul Karim, which is about slide 7, asking, renewable energy is not consistent, meaning it will not always generate the highest capacity. So first, first, why don't they use average renewable energy generated? Second, if we depended on renewables as an energy source and we faced a problem, for example, with the weather that lasted for 2 days, will we be able to compensate for this energy that will not be generated, since we expect that 40 gigawatts of power will be generated by solar PV?
Yeah, that's an excellent question. Okay, very good question. Thank you. The first part is, why don't we use the average? The problem with the electric power grid is that whatever you are producing, whatever your demand requires, on the spot, you have to produce enough electricity to meet that demand. So let me show you this curve here. So if you look at the net load profile, okay, or this curve here, maybe this is better. Here. So the red curve is actually the load profile. This is what the load requires at every point in time. So let's say we are at this time, at this point in time. At this point in time, the load is about 6,000 megawatts. Then at this exact point in time, I have to produce exactly 6,000 megawatts. I cannot take an average. I have to produce exactly 6,000 megawatts at that specific point in time. So if my wind resource is producing less than what I expected to do, then I'll have to produce more from another resource so that the total generation is exactly equal to 6,000 megawatts. So that's the problem, and that creates a problem if you are using renewables. If you have conventional resources like thermal generation, hydro generation, these are all controllable resources. If the load increases, you can increase your power output from your generators. You're going to have no problem. The problem with renewables is that the load might increase, and at the same time, your wind is decreasing. So you will have to compensate for that. And to compensate for that, you either use a flexible resource like hydro, or if you have some stored energy, if you have stored some of the wind energy when the wind was blowing really fast, you store some of that energy, then you can use it when the wind goes down. So that's why we cannot use just the average. Okay. And what was the other question? I forgot.
The second part of the question. Well, you answered the renewable energy. Okay. The second, if we dependent on renewables as an energy source, and we face
what will happen if, okay, I get the question.
Yeah.
Okay, thank you. What will happen if the wind didn't blow for like 2 days? Actually, this is what happened here. So the wind didn't blow during this day here, almost didn't blow. So what happened is that they relied on other resources. So they relied on hydro in their case. In our case, we rely on thermal generation. Unless you have, again, sufficient storage, and sufficient storage to compensate for wind that's not blowing for 1 day is going to be big storage, okay, which is going to be expensive to build for most of the existing storage technologies that are available. There are other ideas, kind of more clever ideas. You can control load. Can I ask the loads, the electric demand, to reduce themselves? Guys, can you reduce your consumption a little bit because we don't have a lot of wind right now? And people are talking about this, and they are actually doing it. It's called demand side management or demand response. It is being done even here in the kingdom. In Saudi Arabia, we have the steel mills, Hadid steel mills. Okay, they are being turned off sometimes if you have a big mismatch between generation and demand. And that's being done even automatically. When the mismatch is big, these arc furnaces at the steel mills, they are being turned off. So these are some of the options that you have when the wind doesn't blow.
Thank you so much, Doctor, for your answer.
Other question?
Take your time. Other question, yes. Muhammad Al-Jadi is asking, which one has more efficiency, battery or hydrogen?
That's a great question. That is very difficult to answer. Yeah, it really depends. Batteries are not one technology. There are different battery types. What is common in batteries is that they are electrochemical devices. You can talk about lithium-ion batteries. You can talk about nickel-cadmium batteries. There are a wide range of battery technologies that are available out there. Now, when it comes to using batteries in combination with the electric power system, using batteries to store energy that is that's coming from wind, maybe people are leaning towards lithium-ion batteries. By the way, lithium-ion batteries are the same batteries that we use in our cell phones, in our laptops, and in electric vehicles. It is kind of the dominant technology right now for these applications. Now, are these more efficient than hydrogen? I'm not sure. I think I'm not a chemical engineer, by the way. I would better consult with a chemical engineer, but my impression is that they are comparable as far as if is concerned. However, hydrogen has a big edge. Most battery technologies tend to have a lot of losses over time. What does that mean? If you are storing energy at 2 p.m. because you have a lot of solar power at 2 p.m. and you would like to use that energy at 7 p.m., then you are storing that energy for like a few hours, 4 or 5 hours. Batteries are okay for this, no problem. But if you are storing energy at 2 p.m. today and you'd like to use it 1 week down the road, batteries are not excellent for this. Then the losses become significant. And that's where hydrogen has a significant edge. Hydrogen is great for seasonal storage. So in Saudi Arabia, for example, we are a summer peaking load. Our load in summer is probably twice as high as our load in winter. Okay, so if we have a lot of renewables, can we store some of the energy that we produce in winter and we use that energy in summer? If you think batteries are terrible for this. Hydrogen can do this quite efficiently. So in that sense, for long-term storage, hydrogen is a lot more efficient. But for short-term storage, my kind of gut feeling is they are kind of comparable. Next question, Ahmed.
Yes, doctor. Yeah, we don't have a name. We have his student number, but he's asking, could you please explain the process of converting the chemical energy of hydrogen to electricity?
What's the question again?
Could you please explain the process of converting the chemical energy of H2 to electricity?
Oh, okay. Well, let me give it a shot. This is it. You just need a fuel cell. A fuel cell is not something new, by the way. The fuel cell technology has been around for decades. I think the first fuel cell was, I don't know, it was built in the 1930 maybe. Okay, but because a fuel cell requires hydrogen as fuel, and hydrogen is not available everywhere, fuel cells are not being very popular. You can think of a fuel cell as a generator. It is a generator, but it does not have any moving parts. And the fuel is hydrogen. Okay, so the way it works, you inject hydrogen, and those of you who are chemical engineers, allow me to talk on your behalf a little bit. I'm not going to do an excellent job, but I'll give it a shot. So you inject hydrogen on one side, on the anode. You inject oxygen on the cathode, and then you have an electrolyte in the middle. So the hydrogen protons will travel through the electrolyte from the anode to the cathode, and the electrons will go through will travel electrically through wires. So if you connect an electric load between the anode and the cathode, if you connect a lamp between the anode or the cathode, the lamp will start to shine. So that is how you convert hydrogen into electricity using a fuel cell. Now, fuel cells come into different types and different sizes and different technologies, and a wide spectrum of technologies actually. and each one of them has advantages, disadvantages, but I can summarize that into two main categories. There are low temperature fuel cells and high temperature fuel cells. The low temperature fuel cells will be able to operate with hydrogen at low temperature. So they don't, for this process, for this chemical process to work, they don't require high temperature. So you can inject low temperature hydrogen, low temperature oxygen, and you will get electricity in response. And these are the fuel cells that are used in fuel cell electric vehicles, because with electric vehicles, you go to the fueling station and they pumped hydrogen into your storage tank, and that hydrogen is going to be at ambient temperature. So you have to use a low temperature fuel cell. And the good news is that low temperature fuel cells are actually cheap fuel cells. They are cheaper fuel cells. So proton exchange membrane and so on, these are kind of the cheaper side. And then there is the high temperature fuel cells, that they cannot accept hydrogen at low temperature because they have to operate at very high temperature. So if you have hydrogen at low temperature, you have to heat it up and then you inject it. Or if you are producing hydrogen from steam methane reforming, the steam methane reforming process, gray hydrogen, blue hydrogen, the steam methane reforming process actually operates at very high temperature. So the hydrogen you produce out of steam methane reforming is actually a very high temperature hydrogen. So if you would like to convert that into electricity, you should use a high temperature fuel cell, like solid oxide fuel cell or other technologies. Hopefully that answers the question very quickly.
Yes, very well, Doctor. Doctor, I think we've reached the end of the session, but if you wish to continue answering the questions, we have actually quite more. So whatever you prefer.
A few more questions.
Okay, sure.
Yeah,
we have a question from Khan.
I can take.
Sorry, I couldn't hear you.
No, go ahead.
Yeah. There's a question from Khan Arfan. I hope I'm spelling it right. He's asking, can you compare efficiency of hydrogen storage in the application of electricity production when we compare it with other energy storages? Examples, batteries, flywheel, and super capacitors.
Yeah, that's a very good question. I think I already answered it partially when I compared hydrogen to batteries, that where hydrogen has a clear edge is in seasonal storage. Batteries cannot compete with hydrogen in seasonal storage. And I would say most of the other storage technologies like flywheels, compressed air, they are not as good as hydrogen for seasonal storage. So if you think about, you guys probably are hearing the news that's coming from Texas about the blackouts that have been taking place for the past several days. Texas is a very warm place, and all of a sudden they are getting through this very low temperature weather in the past week or so, and it's snowing very heavily, and the wind turbines, they have a lot of wind in Texas. The wind turbines are freezing, a lot of snow coming down on the wind turbines, and they stopped rotating, and the wind speed in that case sometimes gets also very, very low. So there is no wind, and the wind turbines themselves are covered by snow, heavy snow. So you get zero power out from wind. Natural gas plants also, they are not getting the natural gas, sufficient natural gas to power up their plants because the natural gas is frozen in their pipes. So huge problem. Now, in these cases, you are going to rely, if there was a storage, you are going to rely on that storage for an extended period of time. And that's where hydrogen, had they have hydrogen, maybe it could have helped. Okay. So as for seasonal storage or for long-term storage, hydrogen is great. In other applications, you're going to find applications where batteries will be performing better. I would claim that for cars, electric vehicles are probably making more sense than hydrogen cars, because in electric vehicles, you are converting, so you plug in the car and you get it charged with electricity from the power outlet. That electricity is stored in a battery, and that battery then powers up an electric motor, an electromechanical motor that drives the wheels. Okay, but if you have a hydrogen car, then you need an additional conversion. You need to convert that hydrogen into electricity using a fuel cell, which is going to be in the car. And then you convert that electricity you take that electricity and power up the motor that drives the wheels. So if you look at the full energy cycle, the electric cars, the pure electric cars, the battery electric cars would be more efficient. And that's actually why you don't see a lot of hydrogen cars so far. Well, that's part of the reason why. And people are more excited about hydrogen vehicles that are big rather than hydrogen vehicles that are small. So if I am going to buy a sedan or a mid-sized SUV, I probably am not going to buy a hydrogen car. But if I'm KFUPM and I have a lot of buses to transport students, then hydrogen would be great, because you can fill up the tank with hydrogen and it will be enough for days. And to fill it up again, it will take a few minutes. While if you are gonna charge an electric bus, it might take hours to charge. So it depends on the application, whether hydrogen is good as storage medium or not. It depends on the application. Another advantage for hydrogen is that if you convert electricity into hydrogen, you don't need to convert it back to electricity. So it is not only a storage medium. Hydrogen is useful in itself. So you can sell hydrogen to an ammonia plant, and in that way you get rid of the other conversion that you need to do. So that's why the hydrogen economy as a complete economy is a very attractive idea. But using hydrogen only for storage might not be the best idea all the time. Next question, Ahmed.
Yes, thank you, Doctor. There's a question from Famra Dufin. He's asking a question referring to slide 11. He's saying, how reliable and economically attractive is the hydrogen and power cogeneration compared to the conventional combined heat and power cogeneration?
Yeah, that's another tough one. Another good question. So we are now comparing combined heat and power. There are two types. There is the conventional combined heat and power. So in that way, you use maybe a gas turbine to produce electricity, but then that will give in the exhaust, that will give a lot of hot exhaust gas. And that exhaust gas can be captured, the heat out of the heat content in the exhaust gas can be captured and can be used to heat up houses, let's say, in cold areas. So that's combined heat and power, for those of you who are not familiar with the term. Now, for that, you can use natural gas. Most of the combined heat and power generators are actually powered up using natural gas. Or you can use hydrogen. Now, you can use hydrogen in two different ways for combined heat and power. You can use hydrogen as a fuel to a natural gas turbine, or to a turbine that's very similar to the natural gas turbine. But instead of injecting natural gas, you inject hydrogen. So you are burning hydrogen, literally, instead of burning natural gas. The advantage of this over burning natural gas is that you don't emit CO2. When you burn hydrogen, there is no CO2 emitted. But when you burn natural gas, there is going to be plenty of CO2 emitted. So from an environmental perspective, the hydrogen CHP, hydrogen-based combined heat and power, will be very environmental friendly, a lot more than natural gas, especially if the hydrogen is produced from a green resource. If hydrogen is produced from electrolysis, then it is coming from a very green resource. Keep in mind that if we are producing hydrogen from, if we are using gray hydrogen, to produce hydrogen, we have emitted CO2 to a lot of CO2 to the environment. So CO2 has been emitted already. And then we burn hydrogen, and then we claim, okay, now we burned hydrogen, we didn't emit CO2. But if it was gray hydrogen, you have already emitted all the CO2 when you created it. Okay, if you are producing, if hydrogen is coming from a blue resource, then CO2 has been emitted, but then it has been stored. And if you are storing it, maybe you are using it for something. So that is a lot better. But of course, the cleanest one will be green hydrogen. In that case, from an environmental standpoint, hydrogen CSP would have a clear edge. As far as efficiency, hydrogen has huge energy content, probably even more than natural gas. As far as efficiency of the CHP unit itself, I think hydrogen will be more efficient. The challenge with hydrogen CHP is how to control, how to capture all the energy that is in the hydrogen, because hydrogen is a lot more dense than natural gas as far as energy is concerned. But I think it is, if it's not more efficient, it would be at least as efficient. This is one way of producing, using CHP from hydrogen. The other way is through fuel cells. So you can inject hydrogen into a fuel cell, and what you will get out of that is actually electricity and heat. And that heat can also be captured. And at that point, the comparison becomes very difficult, because you are comparing an electromechanical device with an electromechanical process with an electrochemical process. So it gets a little bit trickier. So I'll be conservative. I'm not gonna make a comparison here. Okay, Ahmed.
Yes, doctor. Thank you so much. Okay, there's a question from Saeed Abdul Karim again. He's asking about slide 16. Saying R
60. I don't have slide 60, Ahmed.
16, doctor.
16, okay.
Yes.
Yeah.
Yeah, he's asking, are electrolytes similar to batteries?
Are electrolyzers similar to batteries?
Yes.
Yeah, in some sense, they are electrochemical devices. So in that sense, they are similar to batteries, but batteries do not require fuel. Electrolyzers require, well, actually, maybe if I can change the question a little bit. Okay. Maybe if we compare, where is that? This to batteries, that's a more fair comparison, because batteries produce electricity. Fuel cells produce electricity. Electrolyzers do not produce electricity. Electrolyzers consume electricity. So maybe if I may rephrase, if I may rephrase the question, are fuel cells similar to batteries? And the answer is they are both electrochemical devices. However, for a fuel cell to operate, it has to be provided with fuel all the time, and that fuel is hydrogen. But for a battery to operate, it does not have to be provided with fuel. The fuel is already inside the battery, and it will keep operating until the energy inside is consumed, and then at the end it will stop operating, and then it will need to be recharged. So recharged with electric energy. So that's a big difference between a fuel cell and a battery. A fuel cell will keep operating as long as you keep providing it with the fuel, which is hydrogen. So a fuel cell is somewhere between a battery and an electromechanical generator, because it is similar to a battery in the sense that it's electrochemical. It is similar to an electromechanical generator because it requires fuel. An electrolyzer is the opposite of a fuel cell. So you will feed it with electricity and it will give you hydrogen. So I don't think the comparison between that and batteries will be fair. Ahmed?
Yes, doctor. Okay, we have another question from Ahmed Babtain. He's asking, how pure does water have to be for hydrogen generation? The second part is, how does the cost and pollution related to producing water suitable for hydrogen generation affect the issue?
That's another excellent question, which is not being paid attention to very often. When we are going to produce hydrogen using electrolysis, we need water. And if you are in a country like Saudi Arabia, clean water and drinking water is a precious element. It is not available everywhere. We work hard to produce it using desalination. Then you need to start questioning, or at least taking this issue seriously. Where are we going to get the water from? We need plenty of water. We need a lot of water to produce hydrogen from electrolysis. If you are going to do this, and we are going to do this in the kingdom here, then that water cannot come from we cannot use seawater here, because that's going to be too salty. Electrolyzers will fail very quickly if we use seawater. So we have to use desalinated water. And yes, desalinated water consumes energy to be produced. And it depends on how you are powering up the desalination plant. If the desalination plant is not being powered up from a renewable resource, then that will emit CO2 also. Okay, so maybe if we are going to build an electrolysis plant, then we should power up the electrolyzer from the renewable resource, the air separation unit from the renewable resource to get nitrogen, if we are going to convert hydrogen to ammonia, and the desalination plant to produce desalinated water. So that's an issue that is often being underestimated. It is it's overlooked by many people when they talk about electrolysis. Ahmed?
Thank you, doctor. Okay, we have another question from Saeed Abdul Karim. He's saying the renewable energy generated is limited and valuable. So is it better to use it to generate hydrogen, or just to use it as electricity?
Yeah. if you can use it, okay. So here is kind of a rule of thumb. The less conversions you make, the better, because the more conversions, the less efficient you get, right? The more conversions you make, the less efficient your process is. So if the electricity that you produce from the renewable resource can be used directly, it is probably the best option to use it directly without any conversion to anything else. Then why do we convert to hydrogen? We convert to hydrogen because sometimes we don't get enough, sometimes we get enough electricity from the renewable resources, and sometimes we don't. Sometimes we get more than we need. So when we get more than we need, we can store that in the form of hydrogen or in any other storage form, okay? And then when we need it, we can reproduce electricity from whatever we have stored. I'd like to remind you that hydrogen has an additional advantage. Hydrogen in itself is valuable. So if we are going to produce hydrogen from an a renewable resource, I don't need to convert it back to electricity. If I can, that is in itself a valuable product. And that's what NEOM is doing. NEOM is building a huge renewable resource, a lot more than what NEOM as an island, a lot more than what NEOM requires as an island. They'll use that renewable resource only to produce hydrogen. The sole purpose of this is to produce hydrogen. Now, why are they doing this? Because they are not using hydrogen for storage. They are using hydrogen because they think hydrogen is a valuable product. So they'll produce it, they will turn it to ammonia, and they will ship it overseas. So that is the product they are selling. So it is not for storage. So that's a special case. But if you are using hydrogen for storage, you are using it for storage to store whatever is excessive and then turn it back whenever is needed. Ahmed?
Yes, doctor. Okay. We have a question from Mohammed Zaki Al-Smail regarding slide 24.
Mm-hmm.
He's asking, economically, does not that consider too expensive to be built, since we are here in Saudi Arabia, depend on oil, and the project like that are not common here? Or the outcomes later will compensate all that work with benefits?
Yeah. Great question again. Okay, and that's okay. There are multiple dimensions to this issue. A is that today's economy, today's Saudi economy, is heavily reliant on fossil fuels, especially oil. Okay. The plan is to gradually turn away from that, or at least reduce the reliance on oil. So a project like this will help reduce the reliance on oil. That's one aspect. The other aspect is, and we are also producing a very valuable product, and it is an energy product. So instead of producing oil, here we are producing hydrogen or ammonia that is an energy carrier. The other aspect is, you look at all the spikes in oil prices. A few months back, oil producers, the oil prices turned negative. Do you know what that means? That means that some of the oil producers, they had to pay money for the consumers, for the oil consumers, for the consumers to buy that oil. They are being paid to consume that oil. That's how volatile oil prices are getting lately. Okay. Now, yeah, for the past, I would say several weeks or so, oil prices have recovered, and recovered very well, actually. So right now, oil prices are very reasonable in the past several weeks. But just a few months back, oil prices were negative. Okay, so we cannot keep relying on oil. Okay, we have to find other resources. Now, is this the best option? Well, it is one of the options, and it is a good option. And I'll tell you why it's a good option. This is relying on renewable resources. And wind, in NEOM, there is plenty of wind. Solar, in NEOM, there is plenty of sunshine. Okay, so the renewable resources are going to be probably one of the most cost-effective renewable resources in the world, because these resources are put in the right place. That's as far as the renewable resources are concerned. Now, when it comes to customers, who is going to buy? When you are building a project, when you are building a factory, you think, who's going to buy my product, right? So Aramco has just shipped the first shipment of ammonia to Japan just a few months back. So it tells you that ammonia is a valuable product. We already started to ship ammonia to other countries even before the NEOM project is built. Okay, so some specific countries are very interested in buying this product. Japan is one of them. Some of the European countries are also interested for multiple reasons. They use it for their industries. They use it as an energy carrier, and some of the countries are interested in fuel cell transportation. Japan is an example. So these countries, South Korea also, another example. These countries are interested. So you have people who are willing to buy your product. So what is left there is the cost-benefit analysis. You look at what is the price, what is the cost of producing, and you look at what is the price of selling, and you try to break even as soon as possible. Can this be cost-effective? Yes, it can. It probably is cost-effective. Should we do it? I think we should, to diversify our economy. Is this the right time for us to do it? Well, that needs a very careful analysis to see whether you should do this right now or you should do it 5 years down the road. But I'm not surprised that this project is taking place. It could be cost effective, and these are whoever is building this project. This is not the government that's building the project. These are private companies, Air Products and other companies. So they see a feasible investment, I'm sure. Otherwise, they wouldn't have invested. And they are not alone. Let me add this: they are not alone. We have already seen some examples in Germany, in Australia, and in Japan, where they are turning something similar. Ahmed?
Yes, doctor. We have a question from Khan. He's asking, hydrogen explosion represents a considerable hazard. What do you think? How much it will impact hydrogen storage?
Yeah, that is true. I didn't talk about that also. I talked very briefly about storage and storage technologies, and I didn't have time to elaborate on them. So you can store hydrogen as gas or compressed hydrogen, or liquid or solid. The big advantage of liquid and solid is that they are not gas. The big disadvantage of compressed hydrogen is that it is a gas, and this gas is a very explosive gas. You guys probably are aware of hydrogen bombs. So there are nuclear bombs, atomic bombs, and there are hydrogen bombs. This is how bad hydrogen is. It is very explosive. So when it is kept as a gas, safety is a big concern. So they make sure when they build these gas vessels, they make sure that they are very thick, they are very big, they are very secure to minimize the hazard. Now, can you eliminate the hazard? you cannot eliminate the hazard even with the regular cars. With gasoline in gasoline tanks in your car, there is a chance that that gasoline tank might explode. Is the hazard more serious with hydrogen? It probably is. Okay, and that is what makes people turn into liquid hydrogen in the form of ammonia, let's say, or solid hydrogen even. These will minimize that hazard to the minimum. But yeah, it's hydrogen safety is a big subject. It is a subject that's being studied very carefully these days. Ahmed.
Yes. Okay. Ali Al-Shams is asking, what do you think about the future of hydrogen power and vehicles in Saudi Arabia? And will we see them in the next 10 or 20 years?
What do I think of hydrogen power?
Yes. What do you think about the future of hydrogen power and vehicles in Saudi Arabia?
Oh, and vehicles, meaning
Yes,
hydrogen vehicles. Yeah. Yeah. Hydrogen vehicles, let me start with this. I'm not a big fan, to tell the truth, with hydrogen vehicles. Again, especially the small cars. Talking about small cars, I don't think I'm gonna buy a hydrogen car in my lifetime, in the remaining years of my lifetime. I don't think. I think my next car will probably be an electric vehicle, an electric car, but not a hydrogen car. And the reason for that is that the hydrogen, I think I mentioned this before. Hydrogen car requires an additional conversion, and that conversion will take away a good portion of the efficiency of the car. So hydrogen cars might not be very attractive, especially the small cars. Now, when we come to trucks and buses, things are different, because electric buses and electric trucks, there is no good ones as of until now. So all the electric car hype that you are hearing, this is all small cars. This is Tesla and Nissan Leaf or BMW and other companies that are making these small cars for personal use. But when we get to trucks and buses, there is no serious contender for electric trucks or electric buses. This is where hydrogen could have an edge in transportation. So that's as far as transportation is concerned. Now, hydrogen in general, well, I think that's what I spent the whole night trying to convince you guys, that hydrogen is a good idea in general. If you look at the whole hydrogen economy, that consists of multiple components. It consists of using hydrogen for storage. It consists of using hydrogen for industrial applications, for ammonia production, for fertilizers, for decarbonizing the steel industry. Steel industry is one of the heavy emitters of CO2, by the way. And we have a huge steel industry in the kingdom. So to decarbonize the steel industry, hydrogen is a perfect solution. Okay. So if you look at the whole picture, hydrogen seems to be doing great, and it will be doing great in the near future, especially when electrolysis becomes cheaper and cheaper. And I think it will become cheaper and cheaper because renewables, as I showed in my charts, renewables are getting cheaper. Electrolyzers themselves are getting cheaper, which means that this technology will get cheaper over time and will be very competitive. That will make hydrogen economy very attractive. Does that answer that question, Ahmed?
Yes, hopefully. I think it's very well said. Let's take two more questions, if you don't mind. Okay, Ahmed Salim is asking, after few years of after few years, all countries will generate their own power from sun and water. So how it would be a sustainable industry?
Mhm. Well, I'm not sure after a few years that all countries will be able to generate their own power from sun and water. Okay, if you go to the extreme, if you follow the chart that I showed here for renewable prices, renewable cost, the trend is going down. Okay, so if you go to the extreme, these curves are asymptotically reaching zero, but they will never get to zero. That's the time where everything will cost zero money, where energy will cost zero. The cost for energy will be equal to zero, but we'll never get there. I don't think so. Okay, uh, that's A. B is this will actually saturate before it gets to zero. There is a curve here, and let's say the yellow curve here, it is going down and down and down, but eventually it will saturate and it will stop at certain range and it will not keep going down afterwards. Okay, look at the wind. The wind has already almost saturated. So if you extrapolate this is moving down very, very slowly. It is almost stopped there. Okay, so it will not be zero. This is A. B is that these prices are only average prices. So these prices do not apply everywhere. So if you are in Saudi Arabia, you have a lot of sun, alhamdulillah. So because of that, solar prices are getting very low. But if you are in Germany or if you are in the UK, where it is quite cloudy in a lot of times during the year. Okay, if you are in the northwest of the United States, for example, it gets cloudy very often. Actually, it is more cloudy than sunny. Solar will never get there. It is much higher. The solar cost is much higher than the average. Okay, so you'll find countries who are well suited to produce energy this way, and you'll find countries that are not suited to do that. Japan, for example. Why is Japan interested in all this hydrogen stuff? And they are not producing it themselves because they have no space to produce it. If Japan is going to rely on green hydrogen will come basically from solar or wind. And both of these require space, require area on the land. They don't have plenty of area available. Japan is a very congested country. So they don't have that space. So they rely on other countries to provide them with that resource. So not all the countries will get zero free rides. So some people will be producers, some people will be consumers. I agree with you that if the prices go down a lot, then if the cost goes down a lot, then the prices will also be driven down. And if your product is very low, you are not going to make a lot of money. But until we reach there, maybe that will take multiple decades, if not centuries, I would guess, to get there. So I don't think that is a concern in the medium range, let's say in the next 20, 30 years. You still are going to find people interested in buying your product. Ahmed?
Yes. Okay, let's take the last question. Abdullah Namla is asking, is it efficient to burn hydrogen to spin turbines with steam, as we do with diesel?
With this, okay, steam generation. Steam generators usually operate on natural gas or on oil. I'm not aware of steam plants operating on diesel. The the steam generators or the diesel generators are usually not producing steam. These are diesel generators are similar to gas turbine generators. So they are not operating on steam. They are not producing steam. The steam generators, at least the steam generators that are available in Saudi Arabia, are powered up by natural gas most of the time. And some of them are able to operate on oil if need arises. Sometimes you get out of gas, you can replace it with oil. Now, if you replace that with hydrogen, I just said, I think, burning hydrogen does not emit CO2. So if your hydrogen is coming from a renewable resource, then this is a net zero CO2 emitter. Okay, but if you're burning natural gas or oil, you are emitting CO2. If you compare, if the question is asking about hydrogen compared to diesel in diesel generators, diesel is considered a very valuable, a very fine product out of oil. Diesel is coming from oil, okay? So refineries produce several products from oil. One of them is diesel. Diesel is one of the finest products that is produced in refineries. So burning diesel to produce electricity is actually not the best idea, because you can sell this very fine product and make money out of it instead of burning it to produce electricity. Why do we burn diesel to produce electricity? Because diesel is available. You go to any gas station, أي محطة بنزين, and you can buy diesel. Because it is available everywhere, it's available in gas stations, we are using it. We tend to use it to produce electricity. الشباب طالعين البر بياخذوا معهم جنريتر. اوكي يعبوا الجنريتر ديزل في محطة البنزين ويمشوا. Right? So that's why we use diesel. It is not a good idea because it is very expensive compared to other resources. Had we had natural gas available in gas stations, we'd probably have used natural gas instead of diesel. Okay, so if we have hydrogen gas stations, hydrogen fuel stations, okay, I would rather use hydrogen and not use diesel. So yeah, it's now if the question is about efficiency, again, maybe efficiency is comparable whether you use hydrogen or use diesel, as far as the efficiency of the generator itself. Maybe the efficiency is kind of comparable, I guess. Ahmed?
Yes. Well, thank you very much, Doctor, for this insightful webinar and for sharing all this information and knowledge with us and for answering all these questions. And we've taken like a lot of time from you. So thank you. And I'd like to thank all the attendees for attending the webinar. And I hope you all got the most out of it. If you just allow me to share my screen about our social media platforms.
Yeah, go ahead.
Yeah, thank you. You can follow us at Twitter, which is EC_KFUPM, or even at LinkedIn, which is KFUPM Environmental Club. And Doctor, there were a lot of questions asking if you could share with us your slides, if that's possible.
Of course. Yeah, sure.
Yes.
If you should I send it to? Okay, should I send it to Miswar?
Yeah, sure. That would be perfect.
Yeah,
thank you.
I'll send it down.
Thank you very much, Doctor. That's all. Thank you so much, Doctor, for everything.
Okay, thank you, everybody. Thank you for taking the time to attend. If you are interested in this topic, don't hesitate to communicate with me. I left my email will be on my slides, so feel free to drop me an email if you are interested in anything related to hydrogen. Thank you.
Thank you, Doctor.
Mm-hmm.